In this lecture, we'll take up the three examples discussed previously, and we'll see if we can represent the three examples in the state space form that we discussed in the previous lecture, and also I put it up for reference in this top right corner. Okay, so the first task is to choose the state variables and form the state vector. The second task is to form the output vector and the input vector. Well, actually, the input vector and the output vector has already been kind of formed, so we'll see what that is. And once we have this, we'll try to express this system of equations in the form of state space equation to get the corresponding A, B, C, and D matrices. Now, in all the examples that we have taken here, the matrices A, B, C, and D, as you will see as we progress in the lecture, that they are all independent of time and are not time varying. So the system that we considered are time invariant systems, but there can be systems where certain parameters which might be time varying, and hence the matrices A, B, C, D, any of them or all of them can become a time varying quantity, thus making the system under consideration to be a linear time varying system. Okay. In this case, in the model, we will restrict our discussion to these three examples. I strongly suggest that you refer to the existing literature and find out more examples on modeling of such systems and try to represent them in the corresponding state space form. So let us start with the first. System. So we, as a first system, we had the spring mass damper system with the spring coefficient K, B is the damping coefficient, F is the force applied, M is the mass, and Y representing the displacement vector and Y dot representing the velocity. Okay. So we'll choose the state variable as so the first state variable is the displacement y, and the second state variable is the velocity y dot. Okay. Now, if you compare x2 and x1, what essentially we have is the derivative of the variable x1 is nothing but equal to x2, because x2 is y dot. Derivative of x1 is nothing but equal to y dot. Okay, so this comes from the choice of the variables that we have here. Now we'll use the equation that describes the system. So what we have is my double dot plus by dot plus ky to be equal to f. So the input vector is nothing but this force, and the output vector, if I say y, the output vector is nothing but x1 and x2. Okay, and the input vector is just this f. This is there is 1. Now if I write this equation in terms of x1 and x2, what I get is y double dot. Y double dot is what? Is nothing but the derivative of y dot, which means it is the derivative of x2. So what I have is mx2 dot plus by dot. Y dot is nothing but x2, so I have x2 plus ky. Ky is nothing, y is nothing but x1, so I have kx1 to be equal to f. So this gives me that x2 dot is nothing but minus k by m x1 minus b by m x2 plus 1 by m f. Okay. Oh, what I forgot to mention is once we choose the state variables x1 and x2, the state vector is nothing but this. Okay. So now what we have is we have two differential equations. One is x1 dot equal to x2 and another is this equation itself. Okay. So you had a second order system which was represented by the second order ordinary differential equation. Now this has been represented by the use of two first order differential equations. One is in terms of x1 dot and another is for x2 dot. In addition to this, what we have is y to be equal to x1 x2. So this is the output vector. So if I start writing it in terms of the expression that I want, I will have x1 dot x2 dot, which is nothing but my x dot. This will be equal to some 2 cross 2 matrix multiplied by x1 x2 plus some 2 cross 1 matrix multiplied by the input u. Okay, so this is u. Let's see, x1 dot is x2. So what we'll have is x1 dot is 0 times x1 plus 1 times x2 plus 0 times the force F. x2 dot is minus k by m x1. So we have a minus k by m x1 minus b by m x2 minus b by m x2 plus 1 by mf. So you will have a 1 by mf here. So this becomes my A matrix. This becomes my B matrix. Similarly, the output vector that we have, which is y, is nothing but x1 and x2. So this is some matrix multiplied by x1 x2 plus some matrix multiplied by u. Okay, so this is your x, this is your u. So what you have is y is equal to, first one is x1, so you have 1 0. And force component is 0, secondly it is this, and again the force component is 0. So what you have is this is C and this is B. So express this in the terms of x dot equal to ax plus bu and y equal to cx plus du. So this is the state space representation for the spring mass damper system. Okay. This is what we have as the state space representation for the spring mass damper system. We'll move to the next system where we had two masses connected by three springs, two walls on different sides, and the floor that we considered was frictionless and the walls and floor were rigid. Each mass was subject to a force u1 and u2 respectively, and we had the differential equation here. The outputs of interest are y1 and y2. Okay, now, so here what we'll do is we'll choose the first state variable as the first displacement vector and the second state variable as the derivative of y1 dot. Now please note that if you have a second order differential equation, then that differential equation will be related to two state variables. So the order of the ordinary differential equation will be equal to the number of state variables to which it is associated, because we are breaking the nth order or ordinary differential equation to n first order ordinary differential equation. So y1, there is a y1 double dot, so we need two state variables for the first differential equation, and similarly we will need two state variables which are x3 and x4 for the second differential equation. So now what we have is x1 dot to be equal to x2, because y1 dot is nothing but x2, and we also have x3 dot to be equal to x4, because y2 dot is nothing but x4 from the choice of the state variable. So we have two equations right here. Now note that the differential equations that we have, each of them are second order ordinary differential equation, which means I will have four first order differential equation in total to represent the system. So two are here. Now if we use the first differential equation, what I get is m1 y1 double dot is nothing but x2 dot plus k1 y1, so I can replace y1 with x1, plus k2 y1 minus y2, which is nothing but x1 minus x3, to be equal to u1. Similarly, m2 x4 dot plus k1 x3 plus k2 x3 minus x1 will be equal to u2. Now here the state vector x is x1, x2, x3 and x4. I'm using a transpose. The state vector x is x1, x2, x3, x4. The input vector u is u1 and u2 because there are two inputs, and the output vector y is y1 and y2 because we are interested in these two displacement vectors. Okay, so now coming back to the differential equation, we had the two differential equations, x1 dot and x3 dot, and now we have possibly coming up two more differential equations here. So if I write this, I'll have x2 dot to be equal to minus k1 by m1 x1 minus k2 by m1 x1 minus x3 plus 1 by m1 u1, and similarly I'll have x4 dot to be equal to minus k1 by m1 x3, sorry, not m1, m2 x3 minus k2 by m2 x3 minus x1 plus 1 by m2 u2. So this is the another set of differential equations that we have. So now if I start putting them together so that I get it in the term of x dot equal to x plus bu, what I have is x1 dot, x2 dot, x3 dot and x4 dot to be equal to some 4 cross 4 matrix, because we have 4 state variables, or the state vector is of the size 4 cross 1, plus some B matrix multiplied by the input vector This is x, this is h dot. Whatever we get here will be a, whatever we get here will be b, and we have u. So now if I start substituting, what I have x1 dot is equal to x2. So I'll have 0x1, 1x2, 0x3 and 0x4. x2 dot is minus k1 by m1 x1. Then you have one more term as well, minus k2 by m1 coming up. So we have x1 dot to be equal to 0, 1, 0 x1, 1 x2, 0 x3 and 0 x4. x2 dot is minus k1 by m1 minus k2 by m1 x1, 0 x2 plus k2 by m1 x3, 0 x4. I forgot to write the B matrix here. So for B matrix, the first row is 0. The second row is 1 by m1 u1 and 0 u2. And x3 dot is x4, so you have 0, 0, 0, 1 and 0, 0 coming up here. And the third row is k2 by m2 x1, 0 x2 minus k1 by m2 minus k2 by m2 x3, 0 x4, 0 u1 and 1 by m2 u. Okay, so this is what I have as a state in the first differential equation. Now what is the output vector? Output vector that we have, we said that it is I guess we said it is y1 and y2. So y1 and y2 is nothing but x1 and x3. So I can write this as 1 0 0 0 this is my state vector. D will be of the size 2 cross 2. Two outputs. U1. So this is U and this is B. And this should be 0, 0, 1, 0. So this is my C. So C is basically a 2 cross 4 matrix. B is all zeros again in this case. So this is a 2 cross 2 system. Okay. So Y is equal to Cx plus Du. So this here you have is the state space representation of the two mass system that we are discussing. Okay. Similarly, let's go to the third system. In the third system, you have three differential equations. Okay, and all of the differential equations are first order differential equations. So what we'll do is we'll set the first state variable as v1, the second state variable as v2, and the third state variable as the inductor current IL. So what we have is U minus x1 by R is equal to C1 x1 dot plus x3, which implies that x1 dot is nothing but minus x1 by RC minus x3 by C plus U by RC. So this is the first differential equation. Next, you have x3 to be equal to C2 x2 dot, which means that x2 dot is 1 by C x3. This is the second differential equation. Lastly, you have L x3 dot to be equal to x1 minus x2, which implies that x3 dot is 1 by L x1 minus 1 by L x2. This is the second differential equation. So what we have is, in the state space form, x1, x2, x3 dots to be equal to some 3 cross 3 matrix multiplied by x1, x2, x3 plus some 3 cross 1 matrix multiplied by the input u, and the output vector y is what? It is the voltage across capacitor C2. Okay, which is this, which is nothing but x2 in our case. So this will be equal to some 1 cross 3 matrix, which will give me my C plus some 1 cross 1 matrix into B. We'll start with x1 dot. So let's go back. So x1 dot is minus 1 by RC x1, 0 x2 minus 1 by C x3 plus 1 by RC multiplied by U. x2 dot is 0 x1, 0 x2 and 1 by C x3 and 0 U, and x3 dot is 1 by L x1 minus 1 by L x2, 0 x3 and 0 U. So you have your A matrix, this is your state vector, you have your B matrix, this is your input vector. Then what is C matrix? C matrix is 0, 1, 0 because the output is just x2. So this is C, this is your X. D matrix is 0, this is D, and this is your U. So you have X dot equal to Ax plus Bu and Y to be equal to Cx plus D. So this is the state space representation that we have for the above system. Okay. Now there is one interesting thing that you should know is, in the definition of the state variable, I said that it is a fictitious variable that is used to represent the system as a set of first order differential equations and the corresponding algebraic equations. Okay. In all these three examples, so here I have chosen my state vectors to be displacement and the velocity vector. Here I have chosen my state vector to be displacement vector and velocity, displacement and velocity for the first mass and the displacement and velocity for the second mass. And similarly, in the third example, I have chosen my state vector to be the voltage across capacitor 1, voltage across capacitor 2 and the inductor current. Okay, so if you notice that all the state variables that I have chosen have some physical meaning with respect to the system itself. But in general, this need not be true. The state variables need not have any physical meaning. So, for example, in here, you could have used a state variable which was something of this form. So, I'll suggest you try this. Okay. How will the state space representation of this system be if x1 is y plus y dot and x2 is y minus y dot. Okay, so if these are the state variables, similarly I'll pose a question here. How will be the state space representation if x1 is y1 plus y2, x2 is y1 plus y1 dot, x3 is y2 plus y2 dot, and x4 is y2 dot. And for the last case, I'll pose it as this. How will be the state space representation if x1 is v1 minus v2, x2 is il plus v1, x3 is v1 plus. Okay, so try to find out the state space representation. Now what I am trying to say is you can choose these variables properly. If chosen properly, it can be any variable that you want that can express these differential equations, the actual differential equation in terms of a collection of first order differential equations. And this in turn establishes a fact that a state space representation of a system is not unique. In fact, you have infinite number of state space representations for a given system. Why? Because it depends on what is the definition of the state variable that you are taking to describe the system in the state space form. Okay, so once you fix the state variables, then the state space representation is fixed. We'll stop here. Thank you.